If anyone is having a audio problem or video problem, just ping me. I can see the chat. So today we're going to have a webinar here talking about CKB BPM. My name is Xuejie Xiao. I'm a blockchain engineer working for Nervos Foundation, focusing on virtual machine development. If you find my name hard to pronounce, just go by Xiao. That'll work. Today I'm going to give a talk about CKB BPM. Now, a quick reminder here: this is not an introduction. This is not an elementary level talk. We require you to at least know something about Bitcoin, about Ethereum, or about WebAssembly, but we won't require much knowledge about virtual machine. I'll walk you through that one part. First, the agenda here. We'll first talk about what a virtual machine is. Notice there are many different definitions of virtual machine. The exact details might change from one implementation to the another one, but the general idea will apply. We'll introduce virtual machine, the concept of CKB BPM. And then we'll talk about CKB BPM. We'll talk about its design briefly, and most importantly, we'll talk about the design rationale behind CKB BPM. And an important question we get asked a lot is why did we choose Riskfile instruction set as the foundation for CKB BPM instead of going with WebAssembly? I'll use a few minutes here to address that question as well. We expect to spend about 30 minutes on this webinar, and after that, I'll take questions. If you have any questions, feel free to fill in Zoom chat at any time you want. I promise I'll try to answer all of them, but maybe I'll miss one or two. I have to say, I apologize in advance. And if your question didn't get answered, I'll have my contact information at the very last slide. You can contact me or email me, tweet me, anything that'll work. So first thing, let's talk about a virtual machine. So what consists of a virtual machine? First, most importantly, a virtual machine has one or more memory segments. Depending on the exact virtual machine, it may have one big segment for both code and data. Another type of virtual machine may have one segment for code and one segment for data. But the important point is that each virtual machine has at least one memory segment here used to store code and data. And in CKB BPM, we have one big memory segment for storing both. Hence, I'm drawing only one memory segment here. In this memory segment, at each location, we may have a different bytes representing different data. We have 2E here, we have 95 here. And with this memory segment, a virtual machine also has a program counter called the PC register. PC register denotes when the execution is currently on. So in this example, the current execution is on 1234, this memory address. And it means that when we are executing the VM, the next instruction to fetch is at this 1234 location. And with this PC counter here, what we can also have is a bunch of general purpose register. This is where our VM definition can deviate from the other virtual machine definition. Because if you look at different other virtual machine like JVM or WebAssembly, the only thing they have is a stack. They don't have anything called a general purpose register like we have here. But let me assure you, these two are mostly equivalent. So in our example, when we are doing an add or subtract operation, and we are doing the operation between two general purpose registers. On the other hand, for more general purpose stack-based virtual machine, you first put those two operands into the stack, then do an add or subtract based on this stack, based on the stack value here. But this thing are mostly equivalent. We don't have to worry about that one. With this three equipment here, we can show what an instruction looks like at the virtual machine level. So in this example, we can let's assume that this 2E and 95, these two memory bytes, can be translated or can be interpreted as a memory as an add instruction here. So for example, this is based on for example based on Riskfile instruction set, we can translate these two memory bytes into this add A0, A0, and A1 instruction. What it does is that it takes the value in A0 register and the value of A1 register. It add them together and put the final result back into this A0 register. So if we're going to execute this instruction in this virtual machine, we can see here the value A0 gets updated because we're doing a subtraction and we store the value in A0 register. And after that part, we would want this PC pointer to point to the next instruction in the memory segment. And if we continue this loop, we're basically just executing a virtual machine. Now you may wonder, if we just continue executing in a row, this doesn't make much sense. What about loops? What about branches? Let me introduce how a virtual machine implements that part. So all the loops and branches are actually, I should say, most of the loops are branches in the virtual machine is implemented in an instruction called branch instruction. So for example, these 4 memory bytes represent a branch instruction like this. What it does is like it tests the value in A4 and A5 register. If they are the same, it does a branch instruction. The branch location is denoted by the final operand, which means 18 here. So what this instruction means that if A4 and A5 contains the same value, we'll add 18 to the current PC register and jumps to a faraway location. But if A4 and A5 does not equal, we'll skip the branch instruction and just act as if this is normal instruction. So in this first case, we can see that A4 and A5 doesn't have the same value here. So this branch instruction is a mismatch, means that we'll not execute this branch instruction. So what it does is the PC basically just wants to the next part here and continue to execute the next instruction. But if we have a match here in this different example, we have A4 and A5 containing the same value. We'll add 18 here to this PC register and jump to a location far away. With this construct, we can implement loops or conditionals, and actually most of the behavior control we want in a virtual machine. So a summary here. A virtual machine has a 1 or more memory segment, either containing code or data. The second part is for each VM, you have a program counter register denoting the current executing position and where we want to execute next. And depending on the actual virtual machine, it may have a bunch of registers for holding values, or it may have a stack for holding the values. And actually, when we say we are executing a VM, what we did is we take the value at the memory segment pointed by the current program counter, decode that value in a predefined ways, or it could be a WebAssembly encoding spec, it could be a Riskfile instruction set spec. But the point is we're following and provide a spec and decode that value into an instruction, and then we execute the instruction based on predefined meaning. This is how we execute a virtual machine. With this knowledge in mind, let's look at the CKB VM. Due to time limitation, I won't go to every single details about CKB VM. So if you are interested in this topic, I have written an article about CKB VM in much more detail. Feel free to read that article if you want. But the most important fact about CKB VM is that we're following Riskfile standard instruction set. In other words, it means that CKB VM resembles more of a real CPU like an x86 CPU, which is different from, say, like JVM or WebAssembly. This is a very important aspect about CKB VM. We'll explain next why we made this choice. The other thing is that CKB VM's contract will use ELF, the standard ELF format, which is like all the binary you have in your Linux or macOS operating system. This means we can just take existing compilers like LLVM and GCC and use them directly to compile your code into a contract that can be executed on the CKB VM. This means we're trying to gain the broadest industry support here. And for a quick comparison, we can compare CKB VM versus EVM here. Notice I'm comparing CKB VM against EVM, not because EVM is bad or something. I'm making this comparison because EVM is a very general purpose VM. Actually, most of the existing blockchain VM follow the pattern established by Ethereum VM. So that's why we are making this comparison. First thing is, like as I mentioned previously, CKB VM resembles a real CPU. So it works like a real chip in either in our laptops or in your cell phones. On the other hand, EVM resembles more like a JVM. It's like a layer on top of your actual CPU, and you're defining this virtual VM, and you're defining the spec for this VM, and that VM has to run on a real CPU. This is quite different from what CKB BPM chooses to do. The other, for the contract format, CKB also adheres to standard. Actually, I should say that's a practical standard, because everyone's using ELF these days. So CKB BPM will also use ELF. On the other hand, EVM has its own custom format. About two things that for EVM or the other VM like Bitcoin VM, you have to build your own compiler like Solidity or different compiler. On the other hand, CKBM just can use GCC or LVM or any existing compiler. And actually, Rust support for CKBBM actually on the way. There's only a few patches needed in our VM code base, and then we should be able to use Rust to write CKB contracts. Finally, major difference between this part is that we are advocating that you should embed your crypto algorithm in CKBBM. For example, if you're doing ICCP256 key-1 verification, you should embed that part in your contract instead of relying on some existing part in CKB to do the contract. On the other hand, for EVM, we have all this contract pre-built for all the crypto algorithm. This is not, I wouldn't say this is a particular advantage on each side. Each side has its advantage and disadvantage. It's just we're leaning at a different solution because we see a potential we can unleash with this architecture. Now you may ask this question: why is CKB BPM designed in this way? Why did you choose a path which is different from everyone else? Let me make two observations here, and we'll explain why we made this choice. The first observation here is that any feature you have in your blockchain virtual machine will eventually become your legacy. There's no way around that part. I have a few examples here. First thing is that if we look at a Bitcoin scripting language, there's actually a few OP codes that are added to Bitcoin script in the beginning, but later got removed or deprecated or even disabled because there's some vulnerabilities in there. Even though those OP codes has been disabled, there's no way we can get rid of them. They will occupy their OP code and leaving the Bitcoin consensus specification forever. The only way is that we can, when we detect those OP codes, we just halt the contract. There's no way we can get around this part. They're just forever. The other thing is that there used to be some effort about introducing new crypto algorithm into Ethereum. This is one attempt to introduce Blake2B into Ethereum. It got rejected finally, but explain its point. The point I want to make is that we can just introduce a different crypto algorithm in CKB like everyone else does, but where does that lead? We add Blake2B today. Can we make sure that Blake2B will stay relevant like 5 years from now? Are we sure that it's going to stay secure and nobody is going to hack that part? SHA-1 is already broken. And I wonder if maybe 5 or 10 years, we may discover that Blake2B is broken and SHA-3 is broken or SHA-256 is broken. My point is that we can add this thing to our CKB BPM, but the thing is that they will be there forever. If someday people have successfully attacked those crypto algorithms, the only thing we can do is just disable them. There's no way we can remove them from our VM implementation. They're just there forever. The final example is the latest Constantinople hard fork attack thing. And to solve this problem, Ethereum just ended up adding these special rules into the Ethereum VM specification. But the problem is, once we add this rule will be there forever. All future updates to Ethereum will be, if people want to make any new upgrades or a new feature into Ethereum virtual machine, they will have to think about this rule. They will have to think about how the newly added part can interact with this part. Otherwise, we'll run into an attack. So this concludes my point. My first observation here is that any feature we add to a VM will become a legacy. So naturally, we want our VM to be as simple as possible and as long as it can achieve, it's powerful enough to achieve our established goal, that'll be fine. And we want nothing more. The second observation here is that any high-level feature added to a VM will eventually have to become unsafe CPU instruction. This sounds a little bit complicated, but let me break that observation into several parts first. The first part is that no matter how hard we try, assemblies these days in our current CPU architecture are unsafe. We can have all kinds of high-level static verification or all kinds of secure algorithm going on, but at one level, we need to compile this algorithm down to unsafe assemblies. And this year, we have, in the whole 2018, this industry has all been haunted by the spectral and meltdown attack. That means no matter how hard we try, how hard we made our compiler operating system secure, there's also the CPU layer. And on the CPU layer, there's also bugs, and it's not so secure. So we could write our contracts or anything in Haskell or Rust or whatever high-level static verified language we want, but deep down, there will always be one layer that we will need to translate this high-level code into assembly code and run that on our machine. And actually, when we do this translation part, we can. I'm not sure if there's a point that we can make sure this translation will be safe. This is one email I was taking from the Haskell mailing list. There's reference to the original point, and after this talk, I'll share the slide. You can take a look by yourself. The point saying is that the point being made here is that even though we consider Haskell as secure with all the static verification part, Haskell is also vulnerable to its spectral attack, and special measure has to be taken in Haskell to make sure that no program will be vulnerable to this attack. So this concludes the point. And we could do all this translation. We could do all this high-level to low-level translation, but there will be one layer you need to do the translation, and we want that part to have. We don't really want that part to be in our consensus rules. We want that part to be changeable in the future. The final point is that we could also introduce high-level algorithms like ICCB256 key-one verification in our VM or anything like that part, or we could introduce a high-level hash functions and list functions, verification functions in our VM. But the thing is, they're not bug-free. Today we look at our spec and saying, well, this is more or less secure. But tomorrow we may find new bugs in this thing, and we have to do hard forks to run that part. So the thing I'm listing here is just a short portion of all the exploits people have found in Haskell programming language. Is that even though people have tried hard to make Haskell secure, and Haskell, people can only do so much things in Haskell because it's a functional language, deep down in one layer, this is also vulnerable to many different attacks. So I know there's a lot of things to digest, but let me just summarize here. At a fundamental level, if we look at all the history lessons here, we want our blockchain VM to be simple yet powerful. We want it to be able to achieve what we want, and that's it. Once it can achieve our goal, we want it to be as simple as possible, and we want it to be as low level as possible, because in this way, when we build high-level constructs on top of our low-level virtual machine, if there's some bugs or some exploits is found in the high-level part, there's a way we can change that part. And our low level is so simple that we can easily audit that part or verify that part and ensure that it is mostly bug-free, or actually I should say completely bug-free. And the second thing is that we want our virtual blockchain VM to be future-proof. So today there's Blake 2B, today there's SHA-3. But tomorrow, can we guarantee that's enough? 10 years from now, there may be SHA-4, SHA-5, and SHA-3 may be insecure. We want our VM to be able to adapt to that part without us doing any hard fork needed. The third part, which is not mentioned in the above example, is that we want our virtual machine to have reasonable runtime cost model. So, like the Constantinople hard fork shows, many attacks could be performed if we don't have a reasonable runtime cost model. If Theorem doesn't have a reasonable runtime cost model, I have never yet seen a reasonable runtime cost model in WebAssembly. So we definitely want to design a VM that has a reasonable runtime cost model. As I mentioned above, we want a VM to be future-proof, and we want to be able to enable unseen algorithms. We won't be able to know 5 years from now what crypto algorithm will be on the market, but we want our VM to be able to adapt to that part. And to answer all this question, we bring Riskfile on the table. We believe Riskfile is a solution to all the problems we have in designing a blockchain VM. First thing, Riskfile is according to the official website, it's an open ISA enabling a new area of innovation for process architectures. Basically, what it says is that Riskfile is Riskfile designer's goal is to create a new instruction. Basically, sorry, let me rephrase that in a different way. So the goal of Riskfile is to learn from the 50 years of experience designing computer architectures, and design a new architecture that can be applied in the next 50 or even 100 years. And the core spec of Riskfile has been freezed as of May 2017, and this is a very important concept. This is a very important factor for a blockchain VM, because there's no way we can add new spec into Riskfile core, because the core has been freezed. A real hardware has been built on Riskfile, leveraging Riskfile instruction set. So all future changes has to be backward compatible, and we won't need any hard fork to adapt to different things. The next point is that Riskfile is quite simple compared to different instruction set like x86. Riskfile is a 10x simple. 10x because Riskfile only has about 100 instructions as we speak here, but x86 has about 1,000 specs, and at the same time they're equally powerful. So there's no thing that you can do on an x86 CPU, but you couldn't do on Riskfile CPU. And a very important point here is that Riskfile can enable very reasonable and decent runtime cost model. Because Riskfile is a spec that is designed for real hardware, what we can do is we can take a real CPU model, measure the cycle it takes to run each instruction on this CPU, and use that directly as the runtime cost model for this Riskfile CPU. This way, since we are measuring this runtime cost from a real CPU, it's very reasonable and future-proof, because different algorithm will just take more time or less time depending on the CPU cycles it takes to run each instruction in this algorithm. It's a very reasonable runtime cost model. Finally, because Riskfile is just like a real CPU, there's the thing you can do is that you can compile your ICCP verification algorithm into Riskfile assembly, and then just ship that in a crypto algorithm. And maybe tomorrow, if there's a bug in your ICCP library, you just update that library, compile a new contract, and use that to replace the existing contract. There's no hard fork needed in this concept. And with this in mind, let me address this very important question. Why did we choose Riskfile instead of WebAssembly? Let me first say this. We believe WebAssembly is a great thing. WebAssembly has a potential to be very successful, but we only think it's going to be successful in the web space. In the blockchain space, we don't believe WebAssembly is quite fit. Let me explain my point. First thing, so let me explain my point. First thing, WebAssembly is a software spec. Even though it has a spec, there's no way people say that we will guarantee backward compatibility, because to make backward incompatible changes, all WebAssembly needs to do is to gather all the different major browser vendors, make them agree on this change, and they can just each implement this thing in their browser, and boom, we will have a new WebAssembly spec. There's no way preventing them from doing that change. On the other hand, Riskfile is phrased as a hardware spec, which means there will be new hardware using this. There will be hardwares going out every day using this Riskfile spec. And it's impossible to change this spec because you cannot go there and change every single one of the hardware out there. Which brings to the first point. Riskfile is a free spec. WebAssembly is a spec, but that spec is not guaranteed to be stable. The second thing is that Riskfile can enable, as I mentioned above, Riskfile can enable a reasonable and future-proof runtime cost model because we can just measure the cycles taken on a real CPU. On the other hand, up to this point, to the best of my knowledge, I have never seen a reasonable runtime cost model for WebAssembly because it's just a software-defined thing. The browser vendors are busy with their only goal is to make WebAssembly run fast. That goal, making sure WebAssembly has a reasonable runtime cost model is not a goal for WebAssembly spec. So I'm not sure how people are going to handle this problem, but I'm not. I'm just not so optimistic about we can have a reasonable runtime cost model for WebAssembly. The final point is that Riskfile is a small yet powerful feature set, but WebAssembly, if you look at the spec, it only achieves a subset of the functions that Riskfile can enable. One example I can say here is that WebAssembly need to modify the spec in order to have a proper garbage collection algorithm. Well, on the other hand, if we want to have a garbage collection algorithm, we can just compile the implementation in Riskfile into Riskfile assembly and embed in our program, and we will have a program with a garbage collection in Riskfile implementation. On the other hand, that brings a very important questions. So in WebAssembly spec, in the post-MVP features in WebAssembly, there are certain high-level features like garbage collection or threading support. And if at one point this thing becomes mature enough and get added to WebAssembly spec, the blockchain vendors leveraging WebAssembly will need to make a decision. Are they going to implement a garbage collection or threading in their blockchain VM based on WebAssembly? If they do want to do that part, that will be a serious problem because that means a garbage collection implementation will be in their have to be in their consensus rules. They'll have to make sure in all the versions are beyond the garbage collection working the same way. Remember my first observation here. All features you added to our VM will become your legacy. So that means your virtual machine will have to use a freeze the garbage collection algorithm up to this point till forever. There's no way you can change that and make sure you have a deterministic behavior. On the other hand, if they want to exclude this garbage collection and threading support, that means they're not really adhering to WebAssembly spec. That means they're really using a different spec which looks like WebAssembly, but it's not exactly WebAssembly. That's actually one problem I see right now if we're using WebAssembly as a blockchain VM. In short, I think WebAssembly is too big a scope to fit in the blockchain world. In the web world, it has a potential to be successful, but in the blockchain space, we don't believe it's a fit. But yet, people have invested in WebAssembly. As I mentioned above, we believe we have observed this, we have studied the spec, and we believe WebAssembly provides a subset of the features that the Riskfile ISA provides. So here we think on the roadmap we plan to build something that will translate a existing WebAssembly program into Riskfile program. The result is that you can use our existing contract which compiles WebAssembly, then use our transpiler to translate into CKB BPM compatible contract and run them in CKB. So we don't really recommend this route, but I think we can provide this route to help you ease the transition from any existing WebAssembly-based blockchain into our Riskfile-based CKB BPM. And if you look further in this path, we can actually solve this GC problem, because in your WebAssembly program, the GC has to be part of this outside of your program, which is inside their consensus rules. But the thing you can do is that you can compile your WebAssembly program together with a GC garbage collection implementation, and you combine those two parts into a CKB BPM compatible Riskfile program and run that in your CKB BPM. Notice in this final part here, I didn't just say we can implement a GC algorithm. In this path, because the GC algorithm is shipped in your contract, you're actually free to use any GC algorithm. You can even upgrade the GC algorithm. So I believe we can offer something far better than your existing WebAssembly program here. You can just ship any GC algorithm that's tunable for that's tuned for your program, and make sure that your program works better, and include that part and your WebAssembly program together, compile that into Riskfile program, and run that in your CKB BPM. This is something we can achieve. I think we can achieve in our current roadmap. And that's all I have today. If you have any questions, feel free to drop that in chat or something. Or if you want to, actually, another thing I want to mention here is that we're going to record this video. I'll make that public. So any question you share right now, maybe share with others. So if you have something that's so secret you want to say, you can just contact us later. But if you do have something that you want to ask and you think can benefit everyone else, you can just say here. Thank you.